Okay class, in today's session we will talk about how to design the interior panel, and we will also see how to check for the shear forces. Okay, so in the previous class we have calculated we have analyzed the interior panel, and from that we have calculated the bending moment and shear force. Okay, so to design the interior panel, we have to get the design moment and design shear force. So first we will talk about design bending moment, design moment and shear force. Okay, so in IRC 6, they have given the formula to design the ultimate bending moment. Okay, so here you see you have two span. So the interior panel is just like a two-way slab. You have to design the shorter span as well as you have to design the longer span. Okay, so here you know the bending moment in the shorter span and also the bending moment in the longer span. So you need to get the design moment for shorter span as well as for the longer span. Okay, so here we have total design short span ultimate moment equal to MBU. B is related to the shorter span and U is ultimate moment, equal to 1.35 MD plus 1.5 ml. And what is MD? MD is the bending moment in the shorter span due to the dead load, and ml is the bending moment in the shorter span due to live load. So we have calculated in the previous class what is md and what is ml with regards to shorter span. Okay, so I will just substitute the value what we have calculated. 1.35 into md is 3.95 plus 1.5 into 32. So you're getting it as 53.3 kilonewton meter. Okay. Similarly, we need to find the design ultimate moment with regards to longer span. Okay, we'll calculate that. So total ultimate design bending moment with respect to the longer span is denoted by MLU, equal to 1.35 MD plus 1.5 ml. So this MD and this MD are different. This MD is this MD is bending moment due to the dead load with respect to the longer span, and this ML is the bending moment due to live load with respect to the longer span. So whatever MD and ML we have written here, it is with respect to the longer span. Okay, so we have those values. 1.35 into MD is 1.3 plus 1.5 ml is 8.05 equal to 13.83 kilonewton meter. So you got the ultimate design moment. Now you can take this moment and design the section. Okay, we also have to find total design ultimate shear. Total design ultimate shear. Okay, so the formula is VU equal to 1.35 VD. VD is dead load shear force plus 1.5 VL, and VL is live load shear force, equal to 1.35 into 8.81 plus 1.5 into 56.9. This is equal to 97.24 kilonewton. Kilonewton. Okay. Now we need to check the effective depth of slab. We have provided the effective depth of slab. See, the overall depth of the slab is 250 mm, and the effective depth, we can extract the effective depth from that is 220 mm. So we need to check whether whatever the depth of the slab that we have provided in the bridge, is it okay with respect to the strength criteria or not. Okay. So we know that formula. If you have the knowledge of RCC, you will get this formula: effective depth of slab required. Effective depth of slab required. Okay. So D equal to under root mu. You are required to take the maximum moment. You have the shorter span ultimate moment, longer span ultimate moment. So from those two values, you have to take the maximum value here, divided by 0.138 FCKB. Again, it depends on the grade of steel that you are providing. Okay. Equal to mu 53.3 into 10 to the power 6 divided by 0.138. FCK is 25, because the minimum grade of concrete that we provide in the bridge is M25, into, we are considering 1 meter width of the slab, 1000. Okay. So effective depth, you are getting it as 124.3 mm, and the overall depth we have provided is overall depth that we have provided, capital D, equal to 250 mm. If we are assuming that we will be using 12 mm bar, and we will also assume the clear cover. Okay. So small d equal to capital D minus half of the diameter of the bar minus clear cover. Okay. So small d equal to 250 minus, this is coming as 6, minus some clear cover you can provide. So small d, I will take it as 220 mm. So this together it is 30 mm. You can consider it as effective cover. Okay. So small d that we have provided is 220 mm, and the required depth is 124 mm. So whatever depth we have provided, it is okay with respect to the strength criteria, right? Now we can provide AST. You can provide AST using SP16 table, or you can provide AST by using the formula. I will show you that formula. So first we will see how to calculate the area of steel required with respect to the SP16 table. So first we have to write what the material we are using M25 grade concrete and Fe415 steel. So you have to refer SP16 table number 3. Okay. So from that, the PT value you will get PT equal to 0.322. So to get this PT value, you have to refer to mu by BD square. So what is mu? The maximum moment you have to consider 53.3 into 10 to the power 6 divided by 1000 into 220 square. So here you are getting 1.1. For this 1.1 PT value you are getting 0.322. So once you get PT value, what is PT? PT equal to 100 into AST divided by B into D. So you have gotten the PT value. Now you can find AST. AST equal to 0.322 into 1000, that is B, into 220 divided by 100, because it is percentage. This is percentage. So this is equal to 708.4 mm square. If you are not sure how to use SP16s, I will give you one formula. AST by BD equal to 0.5 FCK by Fy under root 1 minus, bracket 1 minus under root 1 minus 4.59 mu divided by FCK BD square. So if you use this formula, more or less you will get the same value. You have to substitute the value of mu, FCK, BD, whatever the things that is given in the formula. You substitute those values and you will get more or less the same value. Okay. Now we can provide the reinforcement. Once we have gotten the AST, we can provide the reinforcement. Okay. So for the shorter span, in the shorter span we have the maximum bending moment. Okay. Provide 12 mm bar at the rate 150 mm center to center. And you know how to find this. So spacing equal to area of 1 bar small AST divided by AST into 1000 width of the slab. So by this formula we are getting a spacing equal to 150 mm center to center. Area of 1 bar, what bar you are assuming? 12 mm bar you are providing. So pi by 4 into 12 square divided by AST. So whatever AST you have calculated, that AST you have to substitute here. So by using this formula, the spacing that you are getting it as 150 mm center to center. For long span, okay, for long span you have to consider the MUL value, the ultimate bending moment with respect to the longer span. Okay, so I'm not same steps you need to follow. I will directly write the spacing for the longer span. Provide 10 mm bar at the rate 150 mm center to center. So this is along longer span. Okay. Now one more check we need to do. We have designed the interior panel of the bridge with respect to the bending moment. So one check we need to do, whether whatever the panel that we have designed, is it okay for the shear force or not? It can resist the shear force or not? That check we need to do. Okay, so in 112 IRC 112 they have given one formula. So I will write that formula for you. VRDC equal to 0.12 K bracket 80 rho 1 FCK raised to 0.33 bracket close into BW into D. where k equal to 1 plus under root 200 divided by small d, which should be less than equal to 2. Okay, so when you substitute the value of d, k value you are getting it as 1.953. And what is rho? Rho, they have given the formula of rho also. Rho rho 1, what? Rho 1 equal to ASL, area of reinforcement provided, BWD, this should be less than equal to 0.02. So what area of reinforcement that you have provided? That is 754 divided by 1000, BW is 1000, into provided D is 220, equal to 0.00343, which is less than 0.02. Okay, so you got the value, you can substitute in VRDC. VRDC is the capacity of the section to resist the shear. Okay, you can substitute here. Put VRDC equal to 0.12 into 1.953 into 80 into rho is 0.00343 into FCK, that is 25 raised to 0.33 bracket closed, into BW, that is 1000, into D is 220. So VRDC you are getting by solving this equation. VRDC you are getting it as 97.34 into 10 to the power 3 Newton, which can be written as 97.34 kilonewton. And the design ultimate shear force is, what is the design ultimate shear force? We have calculated. Design ultimate shear force is 97.24 kilonewton. So the capacity is more than the shear coming, the design shear. Capacity of the shear is 97.34, that is VRDC, and the design ultimate shear force is 97.24. So whatever sections that we have designed, it is okay with respect to the shear force if you are getting this sign. If you are getting this sign, so whatever the section that you have designed, it is okay. It can resist the shear force. Okay. Okay, so we have completed the design of interior panel. In the next class, we will see the analysis of the girder. We will find the bending moment of the girder. So what we have completed till now, we have completed the analysis of the interior panel and we have completed the design of interior panel. So in the next class, we will see how to analyze the girder, the longitudinal girders and the cross girders. Okay, we will see you in the next class. Thank you for watching this video. Thank you very much.